Uh, this section we're going to talk about GPS, but before we do that, let me give you the answer to the break exercise. We're talking about trying to derive the gravitational time dilation formula directly by considering three identical clocks. Two clocks are uh, located at clock one are located gravitational potential phi 1, and the second clock located phi 2. And then we have the third clock uh, dropping, passing these two clocks. When they pass, when it's in place, they can compare time, or rather, they can measure the observer at clock 3 can observe the time at the uh, clock 1 and clock 2, and that from there they can compare and deduce uh, their array is different because they locate at different potentials. Okay. And when the clock 3 passes through the clock 1, it's moving with a velocity u1, or in other words, as far as the clock 3 goes, clock 2 is moving up with minus u1. So therefore, there's a special relativity time dilation effect because uh, tau 1 is the rest frame clock for clock 1, but T3 1 is the clock read by uh, the observer with clock 3. Of course, he sees or she sees the clock 1 is a moving clock, so therefore the rest frame time and here is the moving clock time, and the same way for phi 2. Okay, because uh, now the question is, how is T31 T32 related? They are actually equal because clock 3 is in free fall, so therefore gravity is absent in this inertia frame, and T3 pass with the constant rate, doesn't change. Okay, so therefore these two should be equal. And using the equality of this T31, T32, so the ratio tau 1, tau 2, simply given by the gamma 2, gamma 1. And the gamma, though, is just 1 over square root of 1 minus v squared over c squared. And you take the first term, is simply 1 plus, because it's 2 minus signs, v squared over 2c squared. So therefore, gamma 2 is 1 plus u1 squared over 2c squared, and the gamma 1 is this. Then I can always put the small correction in denominator into numerator by changing the sign. So therefore, equal to 1/2 u1 squared, and of course I still have the plus u squared over 2c squared. So I have this, the ratio of the two times given by the velocity difference. But the velocity difference can be related to gravitational potential difference by simply by energy conservation result of the falling clock 3, because the change in kinetic energy must equal to the minus of the change in potential energy. So 1/2 change in velocity squared equal to minus mass times difference gravitational potential. Of course, m cancels, so therefore the velocity squared difference is given the minus of the potential difference. And this is the result of gravitational uh, time dilation result. Okay. Okay, now we're going to talk about global position systems. Why you absolutely need relativity in order for it to work. Basically, it's a system of uh, at least 24 satellites distributed in 6 even distributed orbits, and the reason we should have at least 4 satellites over the horizon at each point. Okay, and the point is that then the radar signal from the satellite, for example, like you're located here, you like to know where your position is. You like to know what's your position R on the surface of Earth, you receive radar signal from these four satellites, and they these signals contain the information, the location of the satellite, for example, R1, okay, three positions, and the time of trans time of the signal was sent. Okay, same with each of the satellite. And knowing these, I guess, four times four piece of information, then you can plug in this simple equation that the time difference, the distance is equal to c times the time difference. Okay, so therefore you can solve the four unknowns of our location r, which is 1, 2, 3, and time. And so that's the whole idea of a global position system. You can go online, easily find all kinds of information websites. Here is uh, uh, anyway, here I just ran pick one, and you can find more yourself. Anyway, uh, it's actually it's not particular.
This video clip describes properties of the satellite constellation.
Actually, you don't really, it doesn't tell you much about physics. So, but anyway, it tells some technicalities about how to determine the various positions. Uh, but the idea is just this. Okay. So now, why relatively relevant for the operation GPS? Because the distance is measured through timing measurements, and so of the light signal. So therefore, uh, uh, what the distance given by c times delta t. So we need extreme accurate knowledge of the transmission time, because if a nanosecond difference in time can immediately translate into 10 to the minus 9 second times 3 times 10 to the 8 meter per second into zero point 0.3 meters. So that's a foot. Okay, so even nanosecond difference can mean a difference in a foot of this distance. Now, of course, time can be measured by atomic clock to an extremely high accuracy, but you still, because satellites moving at high speed, and it's high up in space, one must take GR and this special alternative time dilation effect into account, because they will make a significant time difference uh, in terms of the accuracy we want to say fixing a position within a few feet. So what are the satellite position and the satellite speed? Speed, of course, in tangential speed. Uh, each satellite is set to have a period of 12 hours. So we set the satellite to go overhead twice a day, and so therefore, knowing that period 12 hours, we can just relate the radial distance to the divided by the velocity by the speed. So therefore, you have one relation between position and velocity. Then also from centripetal force and acceleration, the force is equal to Newton's constant times mass Earth divided by the radius squared, uh, is the force over mass, which is the centripetal acceleration, which is also given by the v squared over r. Okay, so therefore, there's a second relation between position and speed. From this, we can find uh, the radius of satellite is about 3/10 to the 7th meter, or about 4.2 times the radius of Earth, and the speed is about 4 kilometers per second. And knowing this speed, we can find the gamma factor uh, is equal to 1 plus, deviates from 1 by 1 part per 10 billion. Okay, but that's so now let's see. We say that you need time dilation due to relative motion and time dilation due to uh, relative height or gravitational potential difference. So let's look at the relative motion, special relativity correction. Let's hypothetically take a clock at the center of the Earth, the T0. Okay, and so therefore, with respect to you will see the satellite clock is moving, of course. So therefore, there's a special relative time dilation, T gamma 3 times gamma SS satellite gamma factor times this of course is a rest frame in the satellite but moving respect to the center of Earth. Same way for a clock on the surface of Earth, uh, same way. And again, this formula we just seen used in the break exercise. Uh, so now we take because T now is the same, so therefore the ratio of the tau on the Earth compared to the clock, the proper time on the satellite for relative motion is the gamma factor ratio. It's gamma s over gamma over Earth. And then I'm plugging this in here for the gamma factors so into velocity. And then I will put the velocity of the position on the surface of the Earth correction from the denominator to numerator to become minus. So I get this expression. So this is a measure the deviation or the fractional change of uh, the time of on Earth compared with the satellite. So this it says it's about one part in uh, 10, 10 billion. Okay, and when we do this calculation, I just set this equal to 0 because even on the equator, this piece, the, 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 the rotational speed of Earth is much smaller compared to satellite speed. Okay. But anyway, so this is one. So therefore, this ratio is greater than 1. So therefore, we're talking about the satellite clock runs slower. Okay. Now, time dilation due to gravitational time dilation. We have this formula here. Okay, and then I can of course take this. The left hand side is ratio of the time minus 1, so I move the 1 to the other side, so 1 plus this. Okay, and for the gravity potential is simply minus Newton's constant mass of the Earth divided by the radius of the Earth. And for a satellite, similar expression, but it's for the uh, radius of the satellite orbit, and which is 4.2 uh, larger than the radius of the Earth. So therefore, this potential is just Earth's potential, the point on the surface of the Earth divided by 4.2. Then I express the Newton's constant mass over in terms of gravitational acceleration on the surface of Earth g, and then uh, the this term here is simply g over g times the radius of the Earth divided by c squared because okay I have a c squared here, so this 1 minus 4.2, and when I work out this is about 5 10 to the minus 10. Okay, but it's so there's a negative sign here, so it's less than 1, so therefore uh, the satellite clock runs faster. Okay. And of course we can put the time the the ratio of time due to gravitational time dilation and due to relative motion together, get the total full relativity correction. Just multiply these two numbers, and so for the gravitation part, it's uh, just 1 plus this potential difference, and for the relative motion is a minus this. Okay. So anyway, this is the full relative correction for the clock running on Earth and compared to the clock running on the satellite. And in this derivation, we use special relativity time dilation, general relativity time uh, dilation, and you will wonder whether they are somehow separate. No, actually, for full relativist formalism, which we're going to study, gravity is modeled as a curved space-time. It both come out in a scoop. Actually, not surprising, the special relativity is simply due to kinematics, due to the fact we work in space and time. And then the gravity is modeled as curvature of space-time. That's But for curved space-time, it come out in a wash. So in terms of fractional time difference, it was this. If I take this -1, this is the time difference, fraction time difference, and so for due to relative motion is about 10 to the -10, and due to gravitational potential difference is negative. It's about 30 times, 6 times bigger, and but it's on the opposite side. So without taking this relative correction into account, error will rapidly accumulate. I'll give an example. So for a period of just 1 minute, the error due to relative motion, this this number times 60 seconds give you 5 nanoseconds. And the error due to relative height, this 60 second multiplied by this fractional change gives minus 30 nanosecond. So in a minute, you accumulate 25 nanosecond. So remember, a nanosecond change correspond to a foot a distance. So uh, this will make it impossible for locate, you know, within a few feet. Remember, I mentioned that this year this is 100th anniversary of GR. Science magazine have a special issue. Anyway, there was just one short paragraph about GPS. It says, for GPS to function, clocks on satellites on ground have to stay in sync, allowing your smartphones to measure the exact travel time the radio signal from the multiple satellites. The relative timing of the signals allows the phone's GPS receiver to calculate the position. If engineers fail to account for gravity's time dilation, the weaker gravity in orbit would nudge the clock in each GPS satellite ahead of the ground-based clock by 10 microseconds per day, an error that would quickly make the navigation system useless. But just saying, I thought it was very succinct and I think to the point. Okay, so the takeaway of lecture 8 is saying that gravitational time dilation clock at a higher potential will run slower. We originally derived last lecture through gravitational redshift. Now, this time we used the three identical clock, give a more direct derivation. Then we talk about GPS operation requires relative correction because satellite move at high speed and located at high altitude, and and the gravitational effect is about 6 times of the special relativity correction in the opposite direction. The next lecture we're going to say because the clock rate run at different rates, different place, so therefore when the speed you measure will be, of course, will be altered by the different clock rates. So even light speed become position dependent in a gravitational field. Okay, and we can use equivalent principle to calculate the gravitational time deflection, and also we can talk about all these light affected by gravity. So what's the energetics of a gravitational light?